In this example, we're going to explore what happens when sodium hydroxide solution and hydrochloric acid are mixed in a coffee cup calorimeter. Specifically, we're going to determine the enthalpy of this reaction, delta H. Because we're dealing with a reaction whose enthalpy we want to determine, we'd better figure out what our balanced reaction is in the first place. We're going to react sodium hydroxide solution with HCl. This is a double displacement reaction. We should know how to write the products for this reaction already. Sodium chloride and liquid water are formed. There's no need to incorporate any explicit coefficients because everything is balanced as is in this reaction. The next thing that we'll do is recognize how much of each of our reactants we've begun this reaction with. We're told that we have 50 milliliters worth of a solution of sodium hydroxide whose molar concentration is 0.5 molar. 25 milliliters of hydrochloric acid solution whose concentration is likewise 0.5 molar. What this means for us is that given our molarity expression, that molarity is equal to moles of solute per liter of solution, our number of moles of sodium hydroxide is equal to 0.500 molar times the volume in liters, 0.0500 liters. Meaning we have got 0.0250 moles worth of NaOH in this reaction. Similarly, for HCl, we can multiply its molar concentration by the corresponding volume in liters, 0.0250, to determine that we've got 0.0125 moles of HCl. This will become important for us later as we think about which reactant was limiting in this particular case. Notice that because we have fewer moles of hydrochloric acid, our HCl is going to be our limiting reactant in this problem. Overall then, let's think about how much heat was produced from the course of this reaction as written here. We want to know how much heat we got. We need to know this in order to be able to predict what the enthalpy of this reaction were in the first place. To determine how much heat energy we produced in this reaction, we're going to need an equation that describes that heat energy in the first place. An equation that describes quantity of heat could incorporate mass, specific heat capacity, and a change in temperature. Notice that we have a specific heat capacity listed in our problem. We know a change in temperature because we know what a final temperature that this reaction reached was in comparison to the initial temperature of both of our reactants, sodium hydroxide and HCl. We need only to figure out what the total mass of our overall mixture is. Remember that we can use density to this purpose because density is equal to mass over volume. If we mix 50 milliliters of sodium hydroxide solution with 25 milliliters worth of hydrochloric acid solution, and those volumes are additive, then in total we get 75 milliliters of solution. We're told that that solution, that 75 milliliters of mixed sodium hydroxide and HCl, has a density equivalent to water, 1 gram per milliliter. To figure out the mass, we can just multiply 75 by 1. Expect that our final products have a combined total mass of 75 grams. So, in this way, we know the mass, the specific heat capacity, and the temperature change for this mixture. Q is equal to 75 grams multiplied by the specific heat capacity, 4.18 joules per gram degree Celsius, times the temperature change, that's our final temperature, minus our initial temperature, 27.21 degrees C minus 25.0 degrees C. if we multiply all of this stuff out, we ultimately determine that the amount of heat that this mixture produced is 693 joules. Notice that units of grams go away, of degrees Celsius go away. And we're left with joules just like we might anticipate for an energy quantity. From here, how do we determine the enthalpy of reaction? Well, to get an enthalpy, given that Q is equal to 693 joules, we'll determine the enthalpy or delta H for this reaction by placing a negative sign in front of Q and dividing by the number of moles of limiting reactant, N. Why a negative sign? Well, consider that if we were measuring temperature and temperature increased, then any heat energy flowing into that thermometer causing an increase in temperature necessitated heat flowing out of our reaction system. And anytime heat flows out of something, the system's heat has a negative sign corresponding. That means that we're going to keep a negative sign in this equation and divide by the number of moles of limiting reactant. We'd already determined that hydrochloric acid was limiting in this reaction. It was present in a quantity of 0.0125 moles. To get our enthalpy for reaction then, divide negative 693 joules by 0.0125 moles. To 3 significant digits, we end up with 55,400 joules per mole, or more palatably, converting to kilojoules per mole, negative 55.4. This is the enthalpy of reaction for the reaction between sodium hydroxide and hydrochloric acid in this example.